You already know what a jellyfish looks like. You have seen them drift in tide pools, glow under moonlight, wash up on beaches in translucent heaps. You think you understand them. Delicate, harmless, primitive in a way that lets you feel safe in the water. The animal that toddlers draw with a smile. The creature you step over and forget. That familiarity is exactly what makes them so disquieting. They are not mere floaters. They are ancient, living technologies refined across more than 500 million years, predatory, opportunistic, and sometimes devastating in ways we are only beginning to map. What we casually call jellyfish covers an array of bodies and life strategies. Tiny comb jellies no bigger than a thumbnail, colonial siphonophores that act as a single coordinated organism stretching for tens of meters, and box jellies with venom designed to stop a heart. Under their lace of tentacles are microscopic harpoons called nematocysts, spring-loaded cells that fire in microseconds, injecting venom, anchoring prey, and initiating digestion. They do not just sting by accident. In many species, their tentacles sense, aim, and trigger on contact. The image you carry, a bell and a few strings, is one of the most dangerously misleading impressions in our relationship with the ocean. We do not name them flipper. We do not put them in tanks and teach them tricks, because they do not perform for us. We underestimate what evolution built when it built the jelly. The next time you feel the warm shallows, remember that evolution had hundreds of millions of years to refine an animal that kills, invades, engineers ecosystems, and, in some cases, refuses to die. To understand jellyfish, first understand their life cycles. Many species alternate between a sessile polyp stage and a free-swimming medusa stage. A single polyp can clone itself endlessly, producing hundreds of medusae in a process called strobilation. The result: explosive population growth from a single organism. That means a single pier, buoy, or ship hull can seed a bloom that turns a calm bay into a moving carpet of stings within days. Blooms are not random. They are responses to nutrient spikes from agricultural runoff, to warmer water, to the removal of predators by overfishing. Humans have created the conditions that let jellyfish dominate. Their weaponry is subtle and terrifying. Nematocysts are tiny, coiled barbs that, when triggered, uncoil at velocities rivaling bullets and penetrate skin. Venoms vary by species. Some cause localized, excruciating pain. Others target the cardiovascular and nervous systems. Box jellyfish, such as Chironex fleckeri, deliver venom that can cause cardiac arrest within minutes. Irukandji jellyfish, almost invisible, can produce Irukandji syndrome, an insidious, delayed cascade of symptoms: unbearable muscle pain, hypertension, vomiting, and a sensation survivors describe as imminent doom. The animal can be smaller than your fingernail. The consequences can be catastrophic. But poison is only part of the story. Jellyfish are ecosystem engineers. In places where overfishing has removed large predators and competitors, jellyfish bloom unchecked, consuming plankton, fish eggs, and larvae, and creating feedback loops that suppress fish populations. They can convert productive coastal waters into jelly-dominated systems, collapsing local fisheries and reshaping entire food webs. In the Black Sea in the 1980s and 1990s, the invasive comb jelly Nematocysts ledii exploded after being accidentally introduced in ballast water. It consumed massive quantities of fish larvae, contributed to the collapse of anchovy fisheries, and triggered economic and ecological crises that lasted years. They are also efficient invaders. Life stages eggs, polyps, tiny larvae hitch rides on ship hulls and in ballast tanks, surviving long voyages to colonize new seas. Once established, polyps slip into crevices, docks, and cooling intakes, waiting for the exact conditions to reproduce. When those conditions arrive, waste nutrients. Warmer seasons, a microscopic founder can create millions of medusae. The invasion is silent until beaches close, tourism collapses, and fisheries fail. Some jellyfish defy the ordinary rules of life itself. Teratopsis dorni, often called the immortal jellyfish, can revert from an adult medusa back into a juvenile polyp when stressed, essentially restarting its life cycle. Cells transdifferentiate, tissues reorganize, the organism cycles backward. In laboratory conditions, this process has led researchers to call it biologically immortal. It is not conscious immortality, But it is a molecular trick that lets life loop, an unsettling rewrite of aging. And some jelly-like life forms are not single animals at all, but colonies functioning as a single, highly organized unit. The Portuguese man-o'-war looks like a single organism, but is a colony. Floats, stinging tentacles, feeding zooids, and reproductive zooids all specialized and integrated. Siphonophores like Praea dubia stretch for tens of meters as a living assembly line flotation cells, feeding cells, defensive cells, coordinated without a central brain. If one section is damaged, fragments can continue to sting and feed independently. The modularity makes the colony resilient and functionally terrifying. Cut it, and the stinging pieces keep working. We sometimes forget that jellyfish impacts humans directly and dramatically. Stings send tens of thousands to emergency rooms yearly worldwide. Box jellyfish kills have been recorded. In North Queensland, Australia, regular beach warnings and protective nets exist because a single encounter with a box jelly can be fatal. In 2003 and 2006, power plants in Sweden and the United States had to shut down after jellyfish clogged cooling intakes, millions of tiny bells acting together to stop critical infrastructure. Fisheries lose millions of dollars when nets clog with medusae, when catch rates drop due to larval predation, or when markets close because of tainted product exposed to decaying blooms. Their sensory worlds are alien. Jellyfish lack centralized brains. Instead, they have diffused nerve nets, sensory rhopalia, and light-sensing ocelli that allow them to detect light, gravity, and chemicals and coordinate complex behaviors. Some species swim with an elegance that belies intention, adjusting bell contractions and tentacle orientation to maintain depth layers, to ride currents, or to position themselves where prey concentrates. What we call drifting is often finely tuned responsiveness to subtle gradients in the water column. Chemistry is their secret weapon on a broader scale. Jellyfish release compounds that influence local microbial communities, sometimes promoting bacteria that accelerate decay and deplete oxygen as blooms collapse. Species produce mucus that traps plankton, facilitates feeding, or repels predators. Their bodies, rich in protein and gelatin, sink and decay, fueling hypoxic zones that suffocate fish. In extreme bloom collapse events, entire nearshore benthic communities die under a halo of anoxia. The result is patchy dead zones, fisheries declines, and altered nutrient cycling that can persist seasonally or longer. Behaviorally, they can be disturbingly coordinated. Siphonophores and certain aggregating species move in ways that funnel prey and create dense feeding fronts. Jellyfish swarms sometimes synchronize pulsing to create feeding currents powerful enough to corral zooplankton. Even species without obvious coordination can create emergent effects. Thousands of bells passing through a shelf can sweep plankton like a net. When conditions favor them, their collective behavior becomes an invisible machine, reshaping an ecosystem. There are documented episodes that read like ecological horror stories. In the Black Sea, Nemimopsis precipitated fisheries collapse off the coast of Japan. Outbreaks of Nemopolima nomeri, giant jellyfish the size of cars, have clogged fishing nets, ripped through gear, and forced closures. In 2013, Korean fisheries recorded Nemopolima swarms that shut down ports and left fishermen stranded. In the Gulf of Mexico, giant blooms have been linked to increased hypoxia.